So this video is going to look at 8F on applying geometric sequences and starting to create rules for them. So if you remember from 8D, a geometric sequence is when each term is made by multiplying the previous term by a common ratio. So always multiplying by 2 or by 5 or by a third, for example. We can write a general rule for finding the nth term of a geometric sequence, just like we did with arithmetic sequences. And this time the general rule is Tn equals A, so our first term, multiplied by our common ratio to the power of n minus 1. And the reason why we use a power here is, let's for example say that our first number was 3 and then our thing was multiply it by 2. So to get the first time we'd multiply it by 2. To get the third term we'd multiply it by 2 again, multiply it by 2 again, etc. In this case, we could simplify all that to be 3 times 2 cubed. So we can use an index law then to simplify that process. So that's why we have r to the power of n minus 1 in order to solve our equation. So if we have a look here at question 1, it says that given the geometric sequence 4, 20, 100, 500, write a rule for Tn and then find the 10th term in that sequence. So if we look here, you might be able to see that the pattern 4 times 5 gets us 20, times 5 gets us 100, times 5 gets us 500. So we're saying here that A, our first term, is 4, and our common ratio here is 5. So if we write this rule, we're saying Tn, remember the standard form is ARn minus 1, so we can say that Tn is equal to 4 times 5 to the power of n minus 1. And then we can use that rule to find that 10th term. So T10 equals 4 times 5 to the power of 10 minus 1. So that's saying 4 times 5 to the power of 9. And if I pop that in my calculator, 4 times 5 to the power, I can put in the 10 minus 1 if I wanted. I could also do it just with 9, and both times I get 7,812,500. So 7,812,500 is that 10th term in the sequence there for us. What I can then do is I can actually use these to look at percentage change. So if we have a number increasing or decreasing by the same percentage, I've said each day, but it might be each time period, so maybe it's increasing by 5% each year. We can also use a common ratio to represent change, and this is really used if we look at growth and decay in business and the environment. So a classic example is looking at increasing or decreasing populations. If we have an capital R percentage increase, so we're increasing by a certain rate, what that means is our common ratio becomes 1 plus R over 100. We'll use 1 because that represents 100%, so what we were starting with, plus that little bit extra that we're adding on. And if we've got an R percentage reduction, we say that it's 1 minus R over 100. So I'm going to show you how this works here. Question 2, it says state the first 4 terms of a geometric sequence which starts at 150 and each term is 8% more than the previous term. So first of all, we know here that A is 150, that's what we're starting with. We need to find this lowercase r, so our common ratio is 1 plus 8 over 100. Now, we can represent 8 over 100 as 0.08, so we can actually say that this common ratio here is 1.08 to represent we're increasing by 8%. So my rule then for Tn is going to be A, which is 150, times 1.08 to the power of n minus 1. And if I've got to now find the first 4 terms in this sequence, I can substitute in then, so I know that T1 equals 150 times 1.08, 1 minus 1, so that just ends up being 150. T2 is 150 times 1.08 2 to the negative 1, and so I could pop that in my calculator to solve. So 150 times 1.08 to the power of 2 minus 1, which gives me 162. I can then find T3, so this time it's 150 times 1.08 to the power of 3 minus 1, and again T4 now is 150 times 1.08 to the power of 4 minus 1. So I'm just going to, I've already typed this in, I'm just going to change this here where I had my power. So I'll make it 3 and I get 174.96. And if I do it for now 4, I'll just change that there, and I get, it says 2 decimal places, so 188.96. And technically it said give answers to 2 decimal places, so these up here I actually need to add on the 0 zeros. So that there is a percentage increase that I'm working with. I've got the same question here, different numbers, but it's talking about a decrease here because it's 15% less. So this time, my first term is 400, but I've got each term is 15% less than the previous term. So in that case, I need to say that R equals 1 minus 15 over 100, and so that means 1 minus 0.15. So you might have worked out in this case R is going to be 0.85. So when I'm writing my rule this time, Tn equals 400, that's my initial term, times 0.85 times n to the negative 1. And because that R value, remember, is between 0 and 1, I'm going to have a constant decrease that is taking place here. And so I can substitute in to find all those terms. So I can find T1, T2, T3, T4. And I can do 400 times 0.85 to the power of 1 minus 1. I'll just fill all these in for us. And then I can find each of these answers. It says give it to 200 to 2 decimal places. That'll be my first one. My second one, 400 times 0.85 to the power of 2 minus 1. It gives me 340. I'm just going to change this number in the bracket to be 3. I get, oh, don't know what it's done there because it's increased it. 400 times 0.85. Oh, I deleted the power, sorry, to the power of 3 minus 1. So it becomes 289. So 289, and then the final one was 245.65. So I'll just add those decimal places on too. So we can see here each time we are decreasing down, but because it's decreasing 15% less than the previous term, it's not a constant amount that I'm decreasing by. I'm constantly calculating 15% of this term and subtracting it, then 15% here and removing it. So that's why I'm going to use a geometric ratio to solve this. I said before, though, this is used in a real-world example. So we've got here the population in a big city has been recorded as decreasing by 3% each year as people look for a sea change. If the initial population of the city is 5 million, determine the population of the city in 8 years' time. So I want to be able to generate a rule here and then use the rule. Now, it says here the initial population is 5 million, so my A value is 5 million. And R, remember in this case, because it's decreasing, it's going to be 1 minus capital R over 100. Decreasing by 3% each year, so it's minus 3 over 100, so this becomes 0.97. Now, when I'm creating this rule, I'm going to have Tn equals 5 million, so 5 with 6 zeros, times 0.97 n to the power to the power of n minus 1. And if it wants me to find the population in 8 years' time, that wants me to then substitute 8 in for n. So I've got 5 million times 0.97 to the power of 8 minus 1. And if I open up my calculator here, I can type this in. So 5 million times 0.97 to the power of 8 minus 1, or to the power of 7 you could put in. And I get here 4,039,000, so 0.39914. Now, with these questions, because it's talking about population, remember I can't have like half a human or something like that. So it's redundant for me to keep those decimal places. But even if it was 0.6, I can't round that up and create a human. So every time I'm saying that smaller answer, so it'll always round down in this case, because I can't add on a bit more of a human. So in this case, 4,039,914 is the population after 8 years. So we can see then I started with 5 million, so I've lost nearly 1 million people in that 8-year time period. So that there is the end of the summary of 8F. Hopefully from here you continue on and be creating rules in this standard formula of Tn equals V times R to the power of n minus 1. So remember, we want to find that common ratio and the initial term, so then we can write a rule for the sequence in this format. Thank you.